All right, everybody, thanks for coming to SCR's Distinguished Lecture Series. It's my pleasure to introduce Dr. John Brant, Wyoming's very own Department of Civil Engineering. John got his PhD from the University of Nevada, Reno in physical and chemical separation of water, right? 13 years at UW, full professor, and currently he's the director for the Center of Excellence, not mediocrity, for produced water management. So thanks a lot, John, for joining us on fall break.
Thanks.
Yeah.
Thanks, Brad.
Thanks for that.
Well, thanks everybody for taking time out of the day on a Friday. It's semester break nonetheless. Let me talk a little bit about produced water. So, you know, we've heard if you've been in Wyoming or any energy producing state for any amount of time, produced water is something that has no doubt, thanks Bruce, no doubt come to your attention. So I thought today, and I revised the title a little bit from what I had originally proposed, kind of set the stage, give us some context for when we're talking about produced water management. Probably the very first thing that comes to mind is, well, what can we do with the water? And I hope to kind of lay the foundation, or at least set the stage for why maybe we shouldn't just be focusing on the water with our leading strategies or management strategies. Hence my title, Making Sense with Strategic Produced Water Management Approaches. Okay, well, let's start with the definition. Some of you have no doubt seen this ad nauseum, but what is produced water? Well, produced water, regardless of where you're at, is an all-encompassing term for formation water. So that's the water that's been down in the formation from which we're extracting the oil and gas. And in other cases, it can also be a combination of the formation water with any hydraulic fracturing fluids that we put down the hole. And over time, that composition is going to evolve. It's very temporally variable in terms of composition and quantity. That's one of the challenges, as I'll touch back on later on, for treating produced water. Depending on the year, we produce around 21 billion barrels. In the petroleum industry, we use barrels. Describe volumes. I like gallons myself. This equates to about 882 billion gallons per year, or 2.4 billion gallons per day of produced water generated through onshore activities across the United States. Give a little bit more local perspective. Wyoming, which depending on the year, we go from 4th to 6th in terms of the producer volumes here in the U.S., about 2.3 billion barrels per year, or around 3 million gallons per day. As we see here in Colorado, significantly less. And again, that just speaks to the variations in terms of the volumes and even the quantities of produced water that you're going to get back, depending on the formation characteristics and the type of well, conventional versus unconventional that we're using out there in the field. We do a lot of work here at SCR. We're excellent geologists characterizing those formations. So again, our quantity and our quality are incredibly variable. Okay, even for a given well or for two wells located within close proximity, you can get completely different water quality characteristics, and you can get completely different water cuts, or the amount of water of oil that you're going to get. And I want that to stick into your mind, because when we develop a treatment system, those treatment systems really have a narrow range over which we can act, or which we can treat the water efficiently. We're not good at these variations for a variety of reasons. So let's put these produced water volumes into perspective, because when I say 2.whatever billion barrels per year, that sounds like a whole lot of water. And it is a whole lot of water, okay? But it's not quite as much as you might think, okay? So if we're looking at our plot over here on our right, I've got this production volume that's million gallons per day. And I've got some of the different usages here across the state. Irrigation, that's ground plus subsurface withdrawals. industrial consumption, then public water supply, then livestock watering. And then our final column is the amount of produced water we're generating on average, okay, for each year. So typically when we talk about reuse, and I'll hammer on this a little bit, it's, well, hey, let's use it for irrigation. You know, we want to grow things here in Wyoming and all that kind of good stuff. An excellent idea, problematic from a number of perspectives. And we'll tackle the quantity question first. So every day, averaged across the year, we're using about 7,700 million gallons of fresh water for irrigation purposes here in Wyoming. Our produced water volume is around two-ish, okay, 2 to 3 million gallons per day. That equates to about 3% of the annual consumption for irrigators on a daily basis. That's if we use every drop of produced water that we generate in the state, which of course we cannot do. We cannot do that from a treatment perspective because this water is saline. It's about 20,000, 30,000 milligrams per liter. Of course, there are outliers, and that's going to vary from one place to the next. But let's look at the average values there. So we're looking at about a 50% conversion efficiency if we're using reverse osmosis to get that into a freshwater supply. So that 3% now drops to about 1.5%, okay, of the water that we're using for irrigation. It's not to say that it shouldn't be pursued. It's just saying we're not going to solve that issue. Right? We're not going to be able to use it all for irrigation. Public water supply, just put a big X on that. We're never going to use an industrial waste produced water for drinking water. No matter how thirsty we get, way too many hurdles associated with that. Livestock watering, absolutely. This is something that's more viable than irrigation because we have less restrictive TDS requirements for that. And there, we're far exceeding the amount of water, 1,325% of the capacity required for livestock. Okay, so from a volume perspective, can we do good things? Absolutely, we can do good things, but it's not panacea. We can't solve everything. Okay, we can take some small dents there. The other question, and I'll touch on this here in a second, is if we're looking at wells across the state of Wyoming, and the different colors represent the different types of wells. The different types of wells represents different types of waters that we're going to get back from that. But let's just kind of see where are these wells typically focused at. We're looking at the greater Green River Basin and the Powder River Basin, Niobrara, areas like that. And then we can kind of overlap that with where are we using the water, okay? What type of irrigation are we doing? Are we doing crop irrigation? It's the green areas, the green shaded, it's not too much. That's where we're doing our crop irrigation. So, and then we may do some hay growth in Albany and some of our other counties. So there's a distance, right? There's a transportation component for moving that produced water from where we're generating it to where we might want to use it. That's another key variable to keep in mind because water by nature is heavy, right? And heavy things cost lots of fuel to move from point A to point B. And all of that, in addition to our treatment, feeds into this overall cost that we have to consider, whether or not we want to grow hay with rather expensive fresh water. Again, not an ending or an end to our game or an end to our consideration, merely a variable that we have to think about. All right, so I'm starting to paint a little bit of a grim picture here. You're starting to think, well, why in the heck are we even talking about management? Well, there's a lot of other factors that we have to think about, okay? One of those factors, not so much here in Wyoming, but elsewhere, particularly Oklahoma, southern Colorado, places in Texas, is the question of induced seismicity. Okay, so how do we manage our produced water right now? Well, there's primarily two avenues. One is re-injection. You can re-inject the water if you have a suitable formation in which to inject that water. You could use it for enhanced soil recovery sometimes. Or, as we do a lot in the Green River Basin, we do surface impoundments and allow it to naturally evaporate. Each one of those has challenges and opportunities associated with it. One of the challenges that arose, and Fred Scott could correct me on this time, within the last decade, is the question of induced seismicity. When this was first being detected, and here's a map of where we have seen some of the recent earthquakes, USGS, that's the blue areas you can see, it's really focused there in Oklahoma, is we thought, well, this might be due to hydraulic fracture, right? It turns out that's not really the case. A lot of it is pushing this water back into the underlying formations, reactivating some fault lines and other kinds of interesting geological things that I won't embarrass myself talking about. But needless to say, it was a concern amongst the public. Okay, re-injection, which by far is the cheapest avenue for us to get rid of that water because we don't see it anymore. It's no longer a public concern. Then we start to see these earthquakes. So now there was a motivating factor for, hey, you might need to consider something else other than re-injecting it into the subsurface, which we can do for cents on the barrel as opposed to our treatment. That's why it's so nice. But what else? Okay, so earthquakes, I'm not that concerned about it here in Wyoming. Others might be. We figured out ways to, kind of plan for where we're re-injecting or we're not re-injecting. Let's talk dollars and cents. This is what tends to get people's ears pricked up when they have to think about doing something different, moving away from the way we've been doing it for decades. That's our impoundment zone and our re-injection. How much is this costing the industry? Okay, well, and these values are average values. They're rather representative. There again are outliers like anything I'm going to talk about today. Well, acquisition cost for fresh water. Okay, fresh water must be acquired in many cases, at least historically, for fracturing a well. That tends to take between 1 to 5 million gallons per well. So here in Wyoming, we would go, we have several options. We can either drill our own freshwater well. Okay, that's a challenge as we've experienced right for our years, draw down of aquifers. We can buy some water rights from a rancher or some other entity. We can purchase water and transport it to the site from a municipality. Okay, there are other things that we can do. But all of this comes at a cost, and that cost ranges from $6 to $25 per 1,000 gallons. Okay, which if oil is at $125 a barrel, maybe I don't care. If oil is down at $45 a barrel, now I start to care. Right, so it goes with market. The disposal and these costs are primarily representative of re-injection, anywhere from 50 cents to $2.50 per barrel. That, unfortunately, is a lot cheaper than what we're going to get from treatment. Just shatter the surprise there. So it's hard to push past that. And in many cases, my experience with working with industry, if you're not even going to talk about getting below 50 cents a barrel, they don't want to get involved, right? And why would they? Why would they want to pay more? Well, we've got it. Transportation. Now, transportation costs are filling up the truck and moving the water from the well pad to a central collection facility and impoundment, what have you. That comes at a cost, particularly for areas like Wyoming, where we're not a plumbed system. What I mean by a plumbed system is we don't have pipelines that are moving the produced water around. Oklahoma is a plumbed system. It's a little bit easier for them to transport from one site to the next. Here, there's economic costs associated with that. There's environmental costs associated with it as well, from spillage by the truckers themselves and the roads, moving those trucks along previous prairie lines and whatnot. There's erosion aspects, other dust that comes up from those trucks moving on the ground. So now the environmental aspects and then the cost aspects, around $1 a barrel per hour is what we're looking at. Now, treatment, okay, if we want to do treatment for reuse or some other reason, okay, this cost is highly variable. Okay, this cost is going to be a function of the amount of water, the quality of water, and then how clean do I want to get that water. Okay, so these are all variable, and then the size of the facility. Okay, our unit costs are going to go down the bigger the facility, but we kind of made out putting that volume into perspective. It's not really that big when we compare it to a municipal desalination facility. Okay. All right. So these are all things that we have to think about. And with this transportation, I just want to note, if you think about the distances from all of these different wells or where we're initially gathering that produced water, that transportation cost can become significant. Okay, well, again, why manage the water? Well, how much is water worth? That's really the question that we have to ask ourselves. Well, how much it's worth is dependent on how thirsty you really are, right? Okay, if you're super thirsty, you're going to pay a lot of money for that glass of water. And that's where we're moving as a society due to population growth, persistent drought, and other factors that are influencing how much water is available to us. Okay, so this is the drought monitor from September 2021. And you can see, Wyoming's not in the worst shape, but we're certainly not in good shape. Okay, if you haven't kept an eye on the news, you know that the Colorado River system is in jeopardy. Okay, and I'll show some images to kind of push that through. And there's really no signs of relief for that in the intended for the near future. In fact, we're expected to be in a rather prolonged drought pattern here in the Rocky Mountain region. So why show this this image? Really, I'm showing this image to start getting back to that. How thirsty are you? Right? We need water to function, both for our own consumption, but to drive a lot of our industries. So some representative cost, tap water, and these are pulled from Wyoming specifically, about $1.89 per 1,000 gallons. Of course, that cost escalates if you keep track of your water bill as you move beyond a certain consumption point. Desalination I'm putting on there because these waters that we're dealing with are saline waters. Some have TDS of 5,000 milligrams per liter. Others in Oklahoma or Texas may be 200, 300,000 milligrams per liter. A lot of salt in there. That could be an opportunity, and I'll come back to that here in a second. But a seawater desalination system, seawater has a salt content of about 36,000 milligrams per liter. So it's comparable to the produced waters that we have here in Wyoming. The all-in cost, the capital and the operational costs built into that, it gives you about anywhere from $265 to $475 per 1,000 gallons. I treat it, I give you the barrel cost there as well. That's not cheap water, okay? And these are for plants that are greater than 1 million gallons per day in terms of capacity, right? So that far exceeds the size of our distributed produced water facilities. So those costs would be even higher for a produced water system. Municipal wastewater, $1.50 per 1,000 gallons. Then our water that we're using for agricultural production, I didn't put a value here because it's really a function of, hey, am I pulling groundwater? What are my pumping costs? And what are the costs of energy that go into driving that pump? And then, of course, water rights, how senior are you, and so on and so forth. Okay, so there's lots of play in there. But again, how thirsty are you? If a rancher is experiencing a drought, he or she has the option of getting rid of his or her cattle or buying some expensive hay, driving up the price of the meat. This is an recent image of Lake Mead. You can see the famous bathtub ring surrounding that. That's our calcium carbonate that's precipitated over time. Shows you just how much that lake level has dropped and will continue to drop. And what Las Vegas hopes is that it doesn't drop below their most recent intake facility, of which it's getting close. This is a picture of a drought-stricken area here in Wyoming. The cattle is clearly overgrazed on that. That plays into the example I spoke of earlier. Okay, so again, why manage it? Well, we use that water out in the field. This is an image just of fracturing of formation. The more important point here to take away is one of perception. Okay, we are an industry, and if we are perceived, as the public may perceive us, if we're wasting, we have these big impoundments. We're like, wait a minute, you have all this water, you're doing nothing with it. You're taking water out of the system that I could otherwise use. Okay, so we're competing for that resource, right? And so we've got to do a better job of branding ourselves, okay, instead of being wasters of a resource, to utilizers of a resource in any way that we can, okay? All right, so I said treatment's expensive. That's kind of the takeaway thing there. Yes, it is expensive if we're only looking at treating the water to do something with the water. Hopefully, I've at least made the case to where treating the water may not be the most opportune thing for us to do with the produced water itself. Right, so, you know, about 15, 20 years ago, there was a rebranding of municipal wastewater treatment. We went from wastewater treatment facilities to water resource recovery facilities. Okay, there was a reason for doing that, because in municipal wastewater, sure, we have the water and we put that way, clean it, and we put it back into the environment. There's all these great things, but there's also lots of energy in that water. That energy takes the form of all of the organics and the biomass that we grow off of that organics. We can harvest that through an anaerobic digestion process. We can produce biogas. That biogas can then offset the energy consumption of the wastewater treatment facility, or in some cases, we can become net energy positive. Okay, some municipalities will fuel their bus fleets or charge their electric vehicles using the energy produced off of that biogas facility. It's a great way to kind of reimagine wastewater treatment. Also, we collect and produce fertilizers from that wastewater. Great, this is all good stuff. Okay, so if we have that reimagination with our produced water, okay, maybe we can really start to make headway and really move to where we're doing something with this produced water. So here I've got my produced water coming into my unbelievably fancy treatment facility. I think about what are these positive outputs that could come. Okay, low-hanging fruit is water reuse. Low-hanging fruit in terms of that's what we first think about. Resource recovery. There's lots of things in that produced water. It's sat in those rocks for a very long time, leaching things out of that formation that may present some value to us. Energy production. Okay, what does salt water represent? That salt in that water represents chemical energy. That's a chemical potential that we can then generate energy from if we're creative enough. Okay, using processes like pressure retarded osmosis. Then repurposing there on site for our fracturing, which we do, or other industrial purposes there right there on site. Okay. So there's treatment challenges that are going to go into this, but it depends on if we're viewing it as a linear approach or a multi-pronged approach where we're being strategic, okay, and selective in terms of what we're trying to get out of that water. So what's in there, John? Okay, well, let me give you an idea of some of the things that we've come across. Precious metals, precious elements. Something that has received incredible attention here domestically is lithium. Okay, Dr. Parkinson and Hoberg are working on some excellent projects to try and harvest that lithium. Okay, and why do we care about that? Well, green energy is great, but you've got to be able to store those electrons, right? Okay, or the best way to store those electrons right now are the lithium batteries. And I'll show you here in a minute, domestic supplies of lithium don't necessarily match up with our consumptive uses. Iodine, uranium are also present, or can be present. And the other big one are rare earth elements. Rare earth elements are used in all of the electronic devices that we hold near and dear, probably overutilized. And unfortunately, those rare earths, as we'll see in a second, aren't necessarily present a lot here domestically. So we've got to try and better utilize those resources. We touched on the water, the lower, less exotic minerals, rock salts, sodium hydroxide production, and some of the different minerals may or may not have value in the area. And then our other category is, and I'll touch on that later on in our presentation here, is there's a decent amount of hydrocarbons that persist after that gun barrel in our initial separator. That's when we're first processing the produced water there on site. If you've ever been to an impoundment, probably the first thing that you're going to notice is, man, it really smells like a pit of gasoline around here. Somebody please do not light a match. Okay, so anyway, that smell comes from the hydrocarbons that have persisted through the gun barrel. That, to me, is the very first thing that we should probably focus on, because the industry is already positioned to do something with that condensate, okay, and handle that on site. Some of these other things are going to require a reimagination of how we bring in refiners and other people that are skilled in lithium and rare earths and some of the other things. So what's our case here for resource extraction? Well, here's a map focusing on our lithium, okay? Sorry, these are our rare earth elements. China is responsible for about 95% of the world's supply of hard rock mined rare earth elements. 5% is divvied up in other regions of the world or the globe. The United States currently does not have a hard rock mine source of rare earth elements. We used to at one time and went away. So this means that we are heavily reliant on China to give us all of the base materials for making our electronics. The Department of Defense has recognized this and has now made a strategic effort in order to boost our own domestic supplies. That doesn't mean we can find a hard rock source. If we could, we probably would have found it by now. But it means that we can look at less concentrated sources of those rare earths. Hence a study done recently with Fred Scott, Idaho National Labs, where a survey was done across Wyoming and some other places looking for rare earth concentrations, types, etc. And some of our geothermal brines, including our produced waters. Okay, it's there. They're not really rare. They just aren't present in high concentrations, but they are there. If we are creative enough, we can make use of those. So at least for the rare earths, there's a strategic reason, security reason that we have to start to exploit our domestic resources. This is making the same case for our lithium. Okay, and you can see the United States is a net importer of lithium. Next net exporters are Chile, Argentina, some places in Africa. So again, just as you've noticed or you've seen about whole supply chain issues, okay, and why some of you may not get the Christmas presents you want, okay, we are beholden to people sending us resources, and these resources are extremely expensive or extremely important for our day-to-day life, okay, and especially if we want to realize the promise of green energy, okay? So we've got to think outside of the box of where we can maximize these resources. And I propose that produced water and other brines are certainly one of those resources that we can begin to take advantage of. And as we're doing that or taking advantage of that, we can begin to make the economics of treatment more favorable so that industry will pursue it. So I'll come back here and talk a little bit more about the water itself as well and how we should maybe, typically when we think of water reuse, we think of drinking it. Again, we're not going to drink it. There's too many regulatory hurdles associated with that. The cost of treatment would make it the most expensive bottle of water that you've ever had the opportunity to purchase. And finally, getting it from one place to another, from origination to the reuse point, is really just going to make that cost astronomical. So we have to think more locally in terms of how we could reuse that water. Enhanced oil recovery, it's being done. Fracturing, it's already being done. Places in Oklahoma, firefighting is a significant issue. So having reserves around those well pads is something that they really want to see come out. And then irrigation, although the picture seems to show a food crop irrigation, really what I want to drive home is it should be for land reclamation. Your standards will be less strict. It will save the industry money because they won't have to, particularly being here in an arid state, go through multiple seeding events before those seeds take hold, and they can reclaim the land of the former well pads on a much faster basis. You may think, well, none of that is going to take all of the produced water that I've generated. You're absolutely correct. We're not going to do that. And that shouldn't be the vision for our treatment or management facility. We've got to have multiple arrows coming out of our management system. I've said this quite a bit, what are our challenges here? And really the challenges come down to the variation in the quantity, the quality, and the complexity associated with the makeup of that water. So typically, and I've had this question a lot, well, hey, can't you just go out there and take the RO system and desalinate it? Sure, it'll probably operate for 30 minutes before it completely plugs up, and then you're really upset that I went out there spend a lot of your money to build this fancy system, right? It's not going to be that simple. Each site or each collection point is going to require its own approach. Some of those approaches can be simple. Some of those approaches are going to be relatively complex. So we have to have a system that is adaptable to each site. It has to also be a mobile system. It doesn't make much sense to build a fixed system in one location, and then as those wells age, they're no longer bringing you the capacity that you built that system for. You want to be mobile, you want to be adaptable. That adaptation is where our machine learning and our artificial intelligence advancements can really come into play, to where the system itself learns how those water quality and quantity variables change over time, and then how it can adapt its operation set points in order to not plug itself up, for lack of a better term, okay, as it's treating that water, okay, and doing so for the lowest amount of energy investment possible. Resource extraction challenges and opportunities. So typically when we think about the lithium or the rare earths or the calcium carbonate or whatever else I'm trying to get out of that, I say, well, hey, that's worth $100 a ton right now. Let's do it. Okay, well, the system I'm going to build is probably going to be built for 20 odd years, right? And I'm going to finance that system over that time period. So what happens to the price of lithium or rare earths, limestone, or whatever the heck is coming out? It goes up and it goes down with the economy, just like our oil and our gas goes up and it goes down. So if I've built that system and I'm assuming a specific payback period in terms of what I'm trying to extract out of there, and then it doesn't quite meet those beliefs due to a volatile market, I could find myself going belly up. That's the figure that I'm showing here on the left, where I have the market price of some mineral, whatever it is, then the mineral concentration in that water, right? Again, remember the variability in the composition. Okay, so if I haven't planned accordingly, I'm not going to make money off of that system, and I'm going to go belly up, and the whole venture is for naught. So this is where the economists, the geologists, the people that know how that formation in that water is behaving is key ever before I start to design that treatment system. It's a challenge. It's not something we can overcome, but it's definitely something we want to think about, particularly given the variability in our produced waters. Not to be grim, that's just something we have to deal with, right? And we can deal with that, but the opportunity is there. And I love this picture. This is a picture of some Marcellus shale produced water that we were playing around with in the lab. TDS around 350,000 milligrams per liter. So at least an order of magnitude higher than what we deal with here in Miami. Lithium concentration of around 230 milligrams per liter. Okay, that's about double than the highest values we're seeing in some places here in Wyoming. So lots of opportunity. So we've precipitated those solids, and this is out of a 50 milliliter sample. This is all stuff that we potentially, with further processing, we can make some money off of. Okay, particularly with the amount of lithium that's in there. We can take that solid cake, do some solution mining, and begin to recover that lithium. Or we can do other processes, such as the one that Bruce and John are working on. Okay, so the opportunity is there. We just have to see it. And what the reason I love this picture where I started off with is when you're looking at the water sample to begin with, this is all invisible to you. Okay, you're not even going to see that there. We do a few things with our chemistry or different separation technologies. And the opportunity becomes more visual to us. So what are some of the other challenges? Well, market disruption, that's the purpose of that picture there, is there are people, there are mining companies, or there are salt producing companies. They've been doing this for 150 years and they're used to doing it that way, right? And so now you're trying to break into their game, okay, and there's going to be some disruption there. Okay, so you've got to think about, well, how can I synergistically work from me as a produced water person or an oil and gas person to start to get into that market? There's their distribution chains, so on and so forth. And how are we going to entice the oil and gas or the midstream folks to get out of what they've been doing for so many years, to also thinking about, well, hey, there are other resources there that you can make money off. You're going to have to paint you have to be a great marketer, brander for this new endeavor here to really entice them to get into that and get out of what they've been doing for so long. And finally, kind of transitioning to where we're going beyond this is our treatment systems can no longer just be the sledgehammer approach that we've utilized for so long. This is a very visual. This is a filter. I have a cloudy water. I filter it through. The solids are retained, and I get a clean product. Very sledgehammerish, right? It removes everything. Everything's retained. What if I can develop a treatment process or a new material, okay, that can be more selective and target something out of that mixed solution? That is where the gold lies. Okay, if you can start to do that, all of those energy investments and cost about treatment that I spoke about start to really become much more favorable for us. Okay. So here's our treatment system now. Our produced water is coming in. We're applying some different types of processes, or many different types of processes. And here we have our different outputs that we can make money off of, again, depending on scale. We can go through, we're doing our rudimentary treatment, our initial separators, where we can get our hydrocarbons out. Okay, that's coming out first with our new processes. Our minerals, we can go through some type of precipitation process, achieve that. We can desalinate it to get fresh water for some sort of reuse application. That concentrate, we've concentrated the chemical energy in that water. We can generate some energy there. We can get our metals down, or precious metals, other things, or salts down, and do further processing to start to recover those resources. All of this right now with the technology we have is going to be difficult, hence the underscore on the selectivity. Okay, but if we now reimagine from, hey, I just want to treat the water, to a more comprehensive approach looking at all of those different resources, this becomes a much more economically fruitful thing that will be attractive to the industry and the local communities to really start taking it on. These are just some pictures here. Okay, I was doing some snapshots about this is being looked at far beyond the oil and gas industry about how we can better utilize our resources. It's just time for us to really get into this game. So now I'll focus on an area that we've been working on here, the residual hydrocarbons. So this is a Department of Energy project. I won't get too much down into the technical aspects, but just kind of proof of concept, if you will. So again, when we come out of those initial separators, there's plenty of hydrocarbons left. These are some impoundments that we have sampled across the greater Green River Basin in southwest Wyoming. And you can see that the total oil and grease across those impoundments can vary considerably, but it's definitely not a negligible concentration. Now, the exact compounds that are making up that total oil and grease is something yet to be determined, but certainly the VTEX components are rather significant. Our dissolved solids concentration, there's around that 25,000 milligram per liter average that we tend to see coming out of our wells there. So I point that out because if oil and grease fouling is the primary impediment to doing treatment right now, okay, the Neptune facility is a great example of this. Okay, Neptune facility uses this high efficiency reverse osmosis process. They were focused on the salts, but really what killed them was the oil and grease fouling of their initial membrane filters and their ion exchangers. They're battling that on a daily basis. The reason for that is once you get to the smaller emulsion fractions, conventional treatments don't work very well at getting that oil and grease out. The TDS says, hey, if you are able to get that out, we can apply conventional RO or nanofiltration to produce some fresh water. Well, what else? What's another motivating factor there? Well, if you follow air quality standards with the Environmental Protection Agency, you see that southwestern Wyoming is rather constantly in a non-attainment zone for ground level ozone. There's lots of reasons for that ground level ozone production. But again, coming back to those volatiles that are present in those impoundments represent a point source for volatiles that react with sunlight and ultimately get a ground level ozone production. So there's an environmental reason, there's a cost reason, right? If my industry is losing that resource from which they've invested a lot into trying to extract, if I can improve the efficiency of that extraction, I can improve their bottom line. So it's lost revenue. This is just a quick snapshot to say that at our best, centrifugation or the hydrocyclones, we're relegated to some really big oils or emulsions. And that's what typically we would get out during the gun barrel or the initial separators. The smaller stuff, which happens because we're pushing this stuff through valves and other turbulence inducers, that's what persists onto our impoundments and is lost in our current approach. So if we can develop a smarter thing that's not relying on size to separate it out, we might be in business. So we've been exploring developing some new membrane materials using a technique known as electrospinning. And the reason we want to use electrospinning is we have much better control over the physical properties of that membrane, namely in terms of its porosity, pore size, and the like. And then perhaps most important is the surface chemistry. We can make and impart a surface chemistry onto that membrane that selectively goes after our desired phase. That's our hydrocarbons. So the way electrospinning works is we have a solvent polymer solution. We're injecting that solvent polymer solution into across a charge potential. This is a picture of our multi-emitter electrospinner that we're using right now. And we can attach many more heads than this to it. Out of the needles are coming our polymer solution, that cone or Taylor cone that you see. Those are the nanofibers that we're producing to make our membrane. Now, the downside of traditional polymerization techniques with nano additives is aggregation is the Achilles heel, okay, of that kind of approach. Here, we're not relying on the polymerization process. It's happening instantaneously once we leave the emitter, which means that the nanoparticles don't have a chance to aggregate. Okay, and that's really good. So our approach here is to go and make super hydrophobic membranes. Our desire is to permeate the nonpolar, the hydrocarbon phase, while rejecting our water. That's important for a number of reasons. One is we can get a rather purified stream. We're no longer relegated to really big emulsions. We can tackle the smaller emulsions. Also is when we think about sizing a membrane system, we have to think about membrane area. That dictates the size of the facility, ultimately the cost of the facility. So if I want to filter the water through the membrane, I've got a whole lot of water I've got to filter through. If I just want to filter the hydrocarbon phase, volumetrically speaking, that's much, much smaller, which means I can use a much, much smaller facility in order to recover those hydrocarbons out. Okay, so a super hydrophobic surface, that just means that it's not going to like the polar or water phase. It's really going to like the apolar or the hydrocarbon phase, kind of take that out of the solution. So here's an image of our nanocarbon black membrane. That is xylene in water that's been dyed. That's the red phase. You can see as our video rewinds, that xylene really, really likes our membrane. Okay, and we're not even pushing it through. We're just evaluating its absorption capacity for that apolar phase. And as you can notice, okay, it's a very attractive interaction. Okay, so by manipulating that surface chemistry, we can at least achieve our first goal, which is to make it have an affinity for the phase we want to take out of the water. It's being selective. It's not just being selective because of a size relationship, right? Relegate to a sledgehammer type approach. We've evaluated this for all different types of organic solvents and BTEX compounds and the same relationship. So now it's like, okay, well, you can absorb it. You can make an absorbent mat or something like that. Southern California probably really wishes they had during their recent oil spill. But what about the filtration aspect? You can see, as you'll see here in this video, this is a simple representation of membrane filtration. We have a water and a chloroform mixture. The water is dyed blue, the chloroform is dyed red here. And you can see that the chloroform is going to preferentially pass through the membrane while the water is going to be retained. Now, in a practical application, this is going to occur in a cross flow system where we're passing the water over the membrane surface. But it's difficult to get a video of that. So through our testing, we can see that our fluxes are quite high, 2,000 to around 2,500, depending on the properties of the organic solvent. And that's liters per square meter per hour. Typical microfiltration membrane for water is going to operate at a flux of anywhere from 20 to 40 LMH. So these are really high flux values for that organic solvent. And again, that comes down to the favorable interfacial interactions between our membrane and our permeating phase. Okay, well, flux is important, but so too is selectivity. Selectivity means in that permeating phase, how much water is there? Okay, how selective is it for the organic solvent? And the value shown here, greater than or equal to 99%. Practically speaking, in a cross flow system, that drops to around 95 to 96%. That has to do with the pressures that exist in those thin flow channels. Okay. Well, why there's such good fluxes? Well, that comes back to why we used electrospinning to begin with. These filters, unlike conventional polymer filters, have a very high porosity. Okay, they also have a very low tortuosity, which means that the permeating molecule doesn't have to follow a very crooked path as it moves from the feed into the permeate system. Okay, so we've made the distance shorter that it has to travel to get from one point to the next. And that, again, is a real benefit of the electrospun. This just represents kind of what I've already talked about. Is here we have our mixed phase coming in. We've likely concentrated that mixed phase down using a super hydrophilic pretreatment process, which is something we're also working on. We permeate out our condensate. Okay, that's the hydrocarbons that I've been referencing. Just made a rather pure condensate stream, which we're already handling on site. That's why this is so fortuitous, or something that we can explore from a practical standpoint. And then we get a water that's free of these hydrocarbons. Okay, well, what can we do with that? Well, now we can do further processing of the water if we want to use the water for some sort of beneficial application. We can go down to our desalination process, or we can go to our impoundment while reducing the amount of volatiles that we have coming out of that impoundment into the atmosphere. So it's tackling a lot of things. And again, it's not necessarily to just kind of harping on this hydrocarbon separation technique. More is to set the foundation for we can do treatment a lot better. We can do treatment a lot better if we're designing better materials from which to go after some of these incredibly valuable things that we see there in the water. Smarter, less expensive, more adaptable to the energy industry, who really is a important point. This is just a schematic showing how we envision the process going right now after the gun barrel. We'll concentrate down our hydrocarbons using a super hydrophilic membrane. And that's important that it's not like using the word nano here where I'm just trying to sell you something. That super hydrophilic just means that it's highly resistant to oil and grease fouling. Okay, and that's again an Achilles for traditional membranes. Before going to our hydrocarbon recovery process. So we can really think about building this in for anything, our lithium, our rare earth elements, using our smarter technologies. So to summarize, Fred hasn't given me a warning yet, so I assume I'm good on time. Hopefully what I sparked your interest in today. Okay, to move away from just research studies and whatnot, to really gain the attention of the industry and other stakeholders, we have to change our view of what produced water is. Yes, it's water, and water is extremely important and near and dear to my heart. But just because it's near and dear to your heart, if nobody's going to pay you to do it, it's going to just stay, on the bench in the lab. We have to start to broaden out and be smarter about what we're trying to get out of this water. And I believe there's lots of resources, like in our lithiums, our rare earths, other things that can be extracted from there. Okay, and in the near term, okay, we just have to really broaden our imagination and start working across our various disciplines to make sure it's something that we can practically do. And of course, we have to think logistically as well, moving the water, moving the resources that we concentrate down to those that then want to refine it. All of these are transportation or logistical aspects that have to be planned out. Now is the time to do it. And then, you know, the application we've been exploring there, you know, we've had some success in making a quote unquote smart material. Okay, smart just implies selectivity for going and getting one of the many resources that we can. So for that, I really appreciate your time. Hopefully you enjoyed the talk, and feel free to ask questions. And if something pops up later on, glad to speak with you at another time. Thank you.
John's got a question here. Go ahead.
Yeah, hi, it's a very nice presentation. So one question I had was in terms of the current status of the industry participation. What are you looking at in terms, because I think I'm seeing a lot of government agencies being involved here, like DOE, I'm sure, environmental quality. What kind of thing or short term or near term or short term plan that you have?
The federal agencies are putting a lot of money behind this resource extraction, motivated a lot by national security concerns associated with rare earths and some of the other strategic resources that they're looking at. And I'm working with Dr. Hoberg and Dr. Parkinson, another effort there with trying to for lithium, smart lithium recovery. In terms of the industry itself, not seeing a lot of financial interest, but I will say that I'm contacted on almost a weekly basis by midstream folks in Wyoming and Oklahoma, always looking, hey, what else is in there that I can get out to improve my finances? There are some places that they're idling wells right now, even with the price structure as it is, because they have to get the cost of that produced water management down. And there are places right now that they're producing too much water. You know, the water cuts can be 8-to-1 in terms of the oil for the thing. So they've got to do something with all that water, and they don't have a reinjection well. They're stuck with an impoundment. The impoundment has a finite capacity. If I filled that impoundment, I've got to slow down my production on the oil and gas. Okay, so if they can improve the financial structure with their water, then they can open up more wells to make more money. So there's interest in terms of that. But, I don't like to BS people and say, yeah, it's going to be easy for you to get that lithium or rare earths out. It's going to take some investment in terms of time.
Sort of following the same sort of line. Supposing that your work were even more successful than it already is, and you had a really great way to separate out the hydrocarbons from the water, would the industry become interested with a high price on oil and gas or a low price on oil and gas? If it's high, they stand to make more, but they're already making an awful lot of money, so why bother? And if it's low, they're desperate, but it doesn't pay out.
That's a great point. Not necessarily my area of expertise. I think what's really going to be the first motivator for industry is that environmental footprint that we talked about. Regulations with changing administrations are always evolving in terms of how strict they're looking at something. I think that'll be the first motivator. And then when that first starts to happen, nobody wants to be the first when it comes to a separation technology. So they don't want something to go bad. But as it starts to be demonstrated out, I think that adoption will follow for commercial reasons. There's other challenges associated with that oil grease that persist. Clogs up the holding tanks, it's a mess to get out of the transportation trucks. There's a lot of aspects to this. Scott?
So John, I'm super curious about that Marcellus sample that you were working with. At 300 parts per million, that's a pretty complex brine. So that's above saturation for sodium, right? And so probably calcium chloride.
And I think the hardness was around 30,000. Everything was super saturated.
So does the the high concentration of those divalent ions, does that give you trouble when you're trying to do membrane separation?
Oh, you would never do membrane separation
so-
with that. Never.
You would just precipitate out the solids and then work with them that way.
Yeah, you try and do that. So the Marcellus is interesting because re-injection is not really available to them. So that's where you see a lot of the treatment facilities for produced water, and almost all of them, I will say all of them, are some sort of thermal distillation system. Even with that thermal distillation, beyond a TDS of about 50,000 milligrams per liter, reverse osmosis is not practical. Because your recovery drop, you get, you're maybe recovering 20 or 30% of the water for all of that energy and capital that you're putting into there. So once you go beyond that 50-ish threshold, forget about membranes. Okay, people have explored membrane distillation, again, a thermal process where we're using waste heat, but the membrane only serves as a high surface area evaporator rather than a barrier to the salt. So yes, then they go through a chemical precipitation process and they distill the water off.
So it's not too confidential. Can you tell us some examples of the materials or groups on the very surface that make the materials super hydrophilic or super hydrophobic that you use?
Sure. So for the super hydrophobic membrane, it's a polyvinyl difluoride base polymer. That's what we spray our support out with. And then the coating of the surface is nanocarbon black with some PVDF polymer in there to serve as a binder. What makes it super hydrophobic is if you think about the lotus leaf. What the lotus leaf is, or what implies superhydrophobicity, is a combination of surface morphology and surface energy. So you use a low surface energy material like carbon black, and then you have to create a texture or a certain morphology or roughness. And so the reason the lotus leaf is that self-cleaning surface is because it has that low surface energy waxy coating, and then this repeated surface structure here. And that creates a certain wetting regime where the water is trapped at the peaks of those surface structures. Air is beneath, so the water just rolls right off. So you've got to have the right morphology and the right chemistry to achieve that superhydrophobicity. And so for the superhydrophilic membrane, we're using polyacronyl as the base polymer, and then we're using a PANI coating to imply that or create the superhydrophobicity. That just means a contact angle less than 10 degrees, a water contact angle less than 10 degrees. But there's many other ways of going about doing that. Other ones you can explore using that technique, the electrospinning technique. Now, it's not a panacea approach, electrospinning, by the way. There's lots of challenges and nuances that go with getting a good membrane.
So with that in mind, are we gonna be able to recover some elements from if it is not, is it done from effort or probably by finding
Yeah, so there's really two ways for us to view the RO membrane. And the reason that limit comes into play is as you concentrate down the salts, the osmotic pressure gets to the point where you'd have to have extravagant materials to handle the pressures required to keep pushing the water across the membrane. Precipitation, you also will get to a point, even if you try to soften the water, the minimum solubility point for your calcium to start with is around 10, which means you can't precipitate lower than that. You're going to increase that to the point where you get scaling at the end of the system. Now you can do intermediate softening and other things like that. So how can we recover what we want to recover? Well, one, you can try to concentrate it down. Concentrate it down to the point where now you go to another process, okay, where you try to extract it from that concentrated brine. But at least now you've gone from a concentration of 1 microgram per liter to say 100 or 1,000 micrograms per liter. You're just trying to reduce the stress on the downstream process. Or if you're really good, you try to make a membrane that preferentially permeates an ion of a certain, ions of a certain characteristic, so that you get out of this predominantly sodium, chloride, potassium, calcium mixture. And now you're just dealing with a solution of, say, lithium, chloride, and a few other trace type salts. So that's where the smart membrane or the selective membrane can be really good. Right? The hindrance to any of this is material science. That's really where the revolution for treatment is going to come from.
For the TDS with the high ones, like in the 20,000, how does that affect for the biomass processing, if there is any?
You're talking about for the produced water
Yeah.
type thing.
Has there been any research into how it affects it? or-
That's a great question. So I guess similar actually to CSU, and they do a lot of this, of the research on the microorganisms and their entrance there. And you tend to get these pretty extravagant types of organisms that will persist in these ponds and have these salinities. I haven't seen a lot of biomass work outside of just kind of to identify the organisms that are there, because the interest becomes, well, if they're sending it back down whole, are you seeding the hole with bacteria, or the bacteria already there? This is a debatable topic. And then how does that microbiology evolve over time? And our interest there is because we've seen a lot of well casings start to fail because they're being attacked by microorganisms down there. That, to my knowledge, is where a lot of the interest is.
All right. Well, John, I think we're at the end of the hour.
All
I'd
right.
like to thank you for sharing your research today. We've got some SCR swag for you.
Please.